start the recording. Okay, so the session is being recorded now. So good morning, everyone. It's a great pleasure for me to introduce our guest speaker today. Our guest speaker today is Dr. Dario Nucci, who is assistant professor at Tilburg University and Hieronymus Academy of Data Science in Den Bosch. Dario is an active software engineering researcher, and his area of expertise is application of machine learning techniques for software engineering. And this is exactly the topic of his talk today. So without further ado, Dario, the stage is yours. I'm going to mute myself and I'm going to switch off the camera.
Thanks a lot, Alex. So thank you everyone for being here so early. I mean, for me, it's very early. So today I will talk to you briefly about applications of software engineering and actually application machine learning to software engineering. So just to give you some rules, the idea is that I mean, as soon as you have questions, you have doubts, something is not really clear, you can just unmute yourself. Because of technical issues, I cannot see when you type your questions, so Alex and Nathan will tell me the questions. But in all the other cases, please just unmute yourself, it's just easier. So first of all, just one slide about me. So basically, as Alex said, I work in Den Bosch. Yeah, in this period I'm in Italy, but usually I work in Den Bosch. And so I work at the Hieronymus Academy of Data Science. It's a collaboration between the Tilburg University and the Technical University of Eindhoven. But before going to Den Bosch, actually, I was something like an Erasmus. So I traveled a lot in Europe. I started in my home region, so in Molise, that is this place that is in the middle of Italy. And then I moved to the south, so I moved to Salerno, that is even a better place with a lot of sun, a lot of wind. But yes, there's the sea. And then after completing my PhD, I just decided to have a new experience, and then I joined the Vrije University Brussels, and I stayed there for 2 years working on software ecosystems and on pattern mining. And then finally I moved to JADS. What is very important for me is that during all these years I had many collaborations with many people, and Alex is one of those. And actually one of them was in depth, so I moved to the Netherlands a bit before, just because I did several visiting studies in depth. So you don't know anything about JADS. I give you, it's a bit of an advertisement. So JADS, as I was telling you, is the Hieronymus Academy of Data Science, is in Den Bosch, and it's a collaboration between Tilburg University and TUI. So we have a master's that is about data science, and it's about data science and entrepreneurship. And it's in the last years is going very well. So the number of students that we have at JADS is increasing every year. We have many collaboration with different companies. Please consider that we don't work only at the master's level, but we also provide some professional education. We provide PhDs, but the bachelor degree is provided by Tilburg University and TUI. So basically the idea is that you can start your adventure in one of the two mother universities, and then you can just move to Den Bosch if you would like to grasp a bit of entrepreneurship. And here at JADS, I'm working on Radon. So Radon is a project that is funded by the European Union, and it's about serverless computing. So our idea is that we would like to provide a new framework for serverless computing that will allow European industry to use serverless. So, and having all the improvements that you can have with the serverless computing, meaning scalability, better deployability, and this kind of improvements. And actually we're almost at the end of the project. In the next 6 months the project will end, and then it means that in this period we are validating our product. And one of the core parts of this radon framework is about defect prediction. So it's about using machine learning to predict which parts of a data pipeline or of a serverless application can be defective. Talking about JADS, yes, we have many collaborations. So we work with more than 300 companies, and this is why entrepreneurship is really at the core of JADS. Basically, one thing that I really like of JADS is that we have this startup playground. So basically, if you have an idea that is very cool and you like to start a startup, you can do it at JADS. So today we talk about defect prediction. So at the end we talk about using machine learning for software engineering. Now your background is very strong in computer science, so I don't have to tell you that today software is everywhere. I mean, if you think about the current situation, I think that it would have been much worse without the technology that we have right now. Actually, also this lesson could not be possible. Yes, when we talk about software, we know that software can fail. Doesn't matter which operating system you are using, software can fail in very different ways. And actually, if this happens on my machine during a lecture, okay, maybe it's an issue. If I cannot upload a slide, so I cannot see your question, okay, it's another issue that I don't like. But actually, there are many circumstances in which these issues are, I mean, they lead to tragedy. I mean, it's something that you really don't want to. But the real problem is that at this point, okay, you have several ways to test your software, but we still feel that there's something missing. So it's like that we still are not 100% sure that when we deliver a particular piece of software, it will work 100%. And actually today, when we talk about machine learning based systems, this is even worse. So basically it means that we don't know how to test our machine learning product. And this is something that you will see at some point of my presentation. So today we talk about machine learning applications for software engineering, and I will tell you 3 stories. This is why I called the presentation the good, the bad, and the ugly. And this is basically a story that is about first of all defect prediction, then code smell detection, and then how we struggled and tried in the last years to improve these methods. So for each of the characters of these stories, you will see a provocative statement. So the first provocative statement is the one from the good, and actually it is a bit naive as the good. So, and the statement is, okay, after 50 years of software defect prediction, this problem is solved. And I will show you that in the end, it's not solved. And even if we start working on it 50 years ago. Now, first of all, I will provide to you a bit of terminology because it's possible that you never heard about it. First of all, what is a defect? Okay, this is the most clear picture that I have. So every time you work on your software, it's possible that you make an error. So when you're developing your functions, your code, then it's possible that you just enter an error. Now the point is that your user will not see your error, but of course will see failures. So it's possible that, I mean, for example, when I was not able to upload my presentation in a proper way, I didn't see the error, but yes, I noticed the failure. And in the middle, you have something that is called the fault, the bug, the defects. So it's the reason behind the failure that was caused by the error. And actually think about that when we talk about defect, fault, bug, in the end, it's always the same meaning. So really don't care about this part of the terminology. During the presentation, I will say, sometimes I will say bugs, sometimes I will say defects, but in the end, it's the same concept. So as I told you, developers usually introduce bugs. You really cannot do anything. And the real problem is that we are not talking anymore about small pieces of software that are run for research or academic purposes, as people were doing in the 50s. But actually, software is everywhere. And when you have large software systems, and then you have thousands of bugs. And with the large software systems, I talk about Facebook, I talk about Amazon, I talk about Google, and my MacBook. I mean, this kind of software systems. And actually, you could think that if you are a large company as Apple, Google, Amazon, this is not really a problem, because yeah, you have a lot of money, and basically you can hire so many people that they should be able to fix the issues also, because they are very smart. But in the end is that every time we talk about this, you have several limitations. One of the strongest limitation you have is about time. So think about a Formula One car. So if you have a Formula One car, it means that you have a software that is inside the car. But then, so if you have a GP, a Grand Prix every week, like in the last period, it means that every week you have to fix your software issues. And think about, we are talking about monitoring the car, making changes to the car, and this is not something that a driver can survive without. So just think about that in the last Grand Prix, at a certain point, George Russell, that was driving the car for the first time, was asking, yeah, what does this mean in this console? Because I really don't know it. What is this kind of parameter? And actually, that parameter was a particular configuration that he had to put to install on the machine to have the best performance. If you want to know a little more about the relationship between Formula One and software, there's a video that you can see, and it's really about the pressure that these people have to deliver software and to do it in 1 or 2 weeks. It means that in 2 weeks you have to understand what is needed, make the change, test the change, and put it in production. And then the idea of software defect prediction is that, yeah, it would be nice if we could be able to predict which software components are defect prone. Because if I know that a particular piece of code is more inclined to a defect, then I could just investigate it, and I could not waste my time on other software components. While at this point, what you usually do is that you try to investigate the software components that, in your experience, are the most buggy. But how to do it? So there is a lot of literature about defect prediction. In this talk, I will try to summarize as most as possible what I learned in the last 60 years. But of course, please, bear with me that it's possible that there are some parts that are missing. Of course, if during the talk you would like to ask questions, or after the talk you would like to know a bit more, please just contact me. So how to do it? So in practice, what happens is that given a software component, what you can do is to extract some metrics. For example, in this case, we have the CK metrics. Yeah, now I had provided a question for you that I don't know if I can put in. Yes, I can ask. Yes, maybe I can. So my first question is pretty simple. So basically, do you know what is a CK metric? Do you know what we are talking about? Yeah, one more second. Okay, I think that I can publish the results. So some of you don't know what is a CK metric, but this is good because at a certain point in a few slides, I will tell you what it is. So basically, I just think about that a CK metric is a metric that you can use to understand what is the complexity of your piece of code. And in few slides, I will tell you that in the end, when we talk about defect prediction, it's always about the complexity. It is always about trying to understand how much complex is code. But then what we do is not only to extract these metrics, but then we would like to create a model. So usually we have a machine learning model that we train based on past projects, and at the end we can create this model that is able to distinguish which software components are buggy and which software components are not. Otherwise, something else that also is nice and we can do is just to rank the components. So let's say that I have thousands of software components. At the end, I will have a prioritization that I can use to understand which components I should investigate. And the idea is that the ones that are on the top should be investigated before. So as I was telling you, software defect prediction is based on a strong, really strong assumption that the higher the complexity of a code component, the higher is the bug proneness of this code component. Now, the real problem, and think about that, people struggled in understanding what is complexity, because it's a vague theme, a vague term. So. And actually, it's really a jungle. So if you think about software defect prediction, one of the issues we have is that there are so many metrics. And actually, there's not a single study in which basically you have all these metrics and you have an empirical feeling of which one are the best ones. So in brief, you have at least three kinds of alternatives. You have the structural metrics, the process metrics, and the developer metrics. So now I will just give to you an example for each of them, and then we can see which one to apply. So let's start with the structural metrics. So think about that when people started doing this kind of experiments, the Pink Floyd were recording live in Pompeii. So it's really about the 1962. And in the 1962, there is this paper that, in my opinion, is brilliant because it was in the 1962. And actually, it's about the Akiyama equation. And the idea was that maybe if I would like to predict the number of bugs of a software component, what I can do just to create a linear regression model. So let's say that these are my components. And then I know that, for example, for the first component, I have 100 lock, and then I have only 2 bugs. And then I also have this information for all the other components. Maybe what I can try to infer is this kind of logistic regression model, linear regression model. Actually, I could use a logistic regression model as well. And then I could try to verify whether it fits with the new data. Oh, I don't know what happened. Let me open my presentation again. Yeah, actually, I think that for some reason my PowerPoint was reloaded because of an update, but this is another story. Let me find again the slide. Yes, here we are. No. Which screen do you see?
I see both. I mean, I see the present. Oh, now I see the slide, right? Now it's good.
Okay, so as I was telling you, the idea was, okay, maybe I can create a linear model by just infeeding the model from this data. And at the end, Akiyama came up with this equation. This is why it's called the Akiyama equation. That was like the number of bugs is equal to 0.018 multiplied for the number of lock, the lines of code, plus this number 4.86. And now today when we, do you see any issue in this kind of model? So the point is that Akiyama came up with this equation. Naturally, nowadays, if you talk about machine learning and you talk about, you have alluded to this equation, it's a bit hilarious because it's like, you have many threats in this kind of study, and one of them is like, okay, how is possible that based on a few samples, Akiyama was able to derive an equation that could have worked for like all possible software systems. And the problem is that actually Akiyama could not. And indeed, if we think about this kind of model, this is a model that is not highly generalizable. So basically the idea is that, yeah, maybe it works, but it works only on the software system that Akiyama was analyzing. And of course, this is not good because our goal is not to create models, but to use them on our software codes. And then during the years, the people started working on complexity. And one of the first study, and actually we're talking about, we're still in the 70s. And during the 70s, there are at least two really nice work in the area of software complexity. The first one is very well known, is about the McCabe cyclomatic complexity that was delivered in 1976. And then there is the second one that is about the Halstead complexity matrix. Now, because of time, I will focus only the McCabe cyclomatic complexity, but think about that both metrics are about imperative programming. So it's like there are some metrics that you can easily apply to your C code, maybe also to your Python code. But think about when these complexity metrics were delivered, the most well-known programming language was Fortran. We're talking about the time in which Fortran and Ada were the most important languages, and the C was just at the beginning. So the idea is that, and this is the original paper that you can find, is an IEEE transactions on software engineering. And the idea is that, yeah, maybe we can measure the complexity of a program, and what we can do is to try to figure out what is the number of independent paths that are in my source code. Think about that you can do this only if we are talking about really not very containerized piece of code. So basically it works perfectly if we are talking about a single script. It works perfectly if we are talking about C code, Fortran, and Pascal, whatever you want. Or if we are talking about a single method in your Java code, it works. But then what is an independent path? So an independent path is just a path with at least one single edge that has not been traversed before in any other path. So just to provide you an example, so this is the formal definition to compute the McCabe cyclomatic complexity. So the idea is that if we have a graph that represents our code, so if we have a control flow graph, then we can just derive the number of edges, the number of nodes, and then given these two information, we can compute the complexity Another way to compute it is just to understand which are the predicate nodes in our code. So the nodes that have one condition. So, for example, let's have a look to this piece of code. Think about that this is just a control flow graph. So here we have 8 nodes and 9 edges. And then you have 2 predicates. One is the node number 4, and the other one is the node number 5. So it doesn't matter which equation we apply to compute the final results. We can see that we have three different independent paths. The first one is the one that traverse 1, 2, 4, 5, 7, 8. Then there is another one that traverse 1, 2, 4, 3, 2, 4. So there is a cycle. 5, 7, 8, and then there is another one that is the same of the second one, but in which basically at some point we just move from 5 to 6, and then we go back to 7. So this is another strange story. So even if this metric was developed in the 70s, the study that really used it in a really wide way to understand whether this metric was useful for software defect prediction is actually from 2007. So after something like 30 years. And the idea was that Zimmerman tried to evaluate the prediction power of these complexity metrics, and they did it. So he and his co-authors, they did it on different kinds of granularity. And indeed, when you do defect prediction, you can do it at different levels. I mean, the first level is the one we were talking before. It's about understanding in which class of my Java code there is a bug. But then I can also scale down, so I can try to understand which is the method that has a bug, or if I go even much more in detail, I will try to infer which is the line that has a bug. Of course, when the granularity goes down, then you have many more false positives, and then yeah, it's possible that you have to re-elaborate on when you use when you need a technique with a certain level of granularity. But it's important to remind you that at the end in 2007 they discovered that these metrics, they correlate with the defects that you have in Eclipse. That is just the software project that they analyzed. So as I was telling you, all these metrics, they work very well in imperative programming, and we are talking about code that was developed in Fortran, ADA, or in C. But then in the 90s, you have the object-oriented programming revolution, and so as after a few years, Serebrenik and McCabe developed this set of metrics that is called the CK metrics because of the two main authors that actually are still the most well-known in software metrics to understand the complexity of some software components. So there are in general, in this paper, they presented 8 different metrics. You can find the catalog online, and actually also during the years, many more metrics were added. But in this talk, I will provide you only one example. And the example is about the metric that is called LCOM, or lack of cohesion in methods. So let's consider a class. In this class, we have different methods, M1, M2, Mn. And the idea is that we like to compute the set, I mean, for each method, then you have a set of instance variables. that we can just call II, and we have one of these sets. We have one set for each method. So at the end we have n sets, and the outcome is the number of disjoint sets that are formed by the intersection of these sets. Now, just to provide you a brief example, because I think that if you have a look to the example, it's much easier to understand. The idea is that, so let's consider this piece of code, this class. In this class, we have 4 different attributes, F1, F2, F3, and F4, and then we have 3 methods. And as you can see, this is just some pseudocode, but let's assume that the first method is using 2 attributes. The second one is using another 2, so it's using F2 and F3, and then the last one is using F3 and F4. Then we can easily compute the sets we were talking about. So basically, I1 is composed of F1, F2, F2 is composed of F2, F3, and I3 is composed of F3, F4. Now we have to compute the disjoint sets. And naturally, the one between I1 and I2 is composed of only F2. And then we have an empty set that is between the I1 and I3. And then the last disjoint set is between I2 and I3, and is composed of F3. So if we want to compute the number of empty disjoint sets, this number is 1. And yeah, then the point, I mean, the question at this point is, okay, why? Why I should care about this number? What does it represent? And the idea is that, having only this number, it's really hard to say anything. But if you consider also other software components, then you can try to relate the metric in the different software components. And the idea is that the higher the outcome, the higher is the lack of cohesion between methods. It means that you have different methods that are not communicating. So basically, they could be split in different classes. So as I was telling you, think about during the years there were many definitions of this kind of metrics. You can find many more metrics nowadays. So every time we talk about software metrics, please first consider the definition. It's even if we only talk about lack of cohesion in methods, there are at least 3 different definitions of this metric, and then the way is defined. You have to understand the definition to use it, because otherwise is useless to have a look to these metrics. And actually, these metrics were used also in the context of defect prediction. And there is this paper from 1996, which they tried to understand whether you could use these metrics in software defect prediction. And in the end, they verified as well that these metrics, they have a prediction power. Of course, there are some metrics that have a better correlation. For example, the depth of inheritance tree, the number of children of a class, the coupling between the different objects, so the coupling between the different methods. But then there are also some metrics that are less usable. For example, the lack of cohesion of methods I was talking about. But at the beginning, I told you that was more or less a jungle. So, I wish we would have only structural metrics, but in the end, the structural metrics, they don't provide the full picture. And so some other metrics were proposed, and one of them is called process metrics. So the idea is that we don't care anymore the single software component. At least we don't care about digging in analyzing the software component and the information like the number of branches, the number of edges, the number of nodes that you have in your software component. But at this point, we really care about the process. So let's say that in my GitHub repository, I have only 2 files, and then I start committing and pushing changes. Then for each of these files, I will have a different number of changes, and it's possible that in a commit I push like only 1 file, and then in another one I push 10 different files, and this is something that is called the commit size. And then actually it's also important to try to understand together how many components are pushing and how they are related to each other. So it's about trying to understand what is the entropy of the change that I'm inserting when I push my code in GitHub. So in this presentation, I will focus only on the number of changes. That is actually the simplest metrics, but the simplest metric. But you can find many papers that are in this context. And actually, as I was telling you, if you have any other question, just you can just ping me, or we can just talk during the pause. So in 2008, there was a really nice comprehensive study that is on the role of product and process metrics. So the idea was to try, think about it, that we are in 2008. So the product metrics were already there, were already been analyzed. And then Moser, Pedritz, and Nucci, they tried to understand, okay, but let's say that I have some product metrics, and I can extract these product metrics from my code. And now let's say that I can compute also some metrics like the number of changes. Now, which one should I use? Should I rely on product metrics or on process metrics? And then the results of their study demonstrated that, at least on the projects they analyzed, the pass faults and the number of changes are better indicator than the structural metrics. So basically, it means that it doesn't matter what is the, at least from this paper, it means that it doesn't matter how many, what is the complexity of a single component, but what really matters is the number of faults that this component had in the past, or the number of changes that were applied to this component in the past. But at this point, we are still missing what I think is the most important thing in a software development process, that is the developer. So at this point, we are still thinking about, the rationale at this point is like, okay, it doesn't matter who is introducing the change. All the developers are the same, which is hard to believe. So basically, we are saying we are not considering the experience of the developer. We are not experimenting if there are like communication issues between the developers. So for this reason, another set of metrics was developed, and in this case, we talk about developer metrics. So there are many metrics also for this set, and this is why I at the beginning I say that it's really a jungle, but the idea is that at least the one that is very easy to compute is the number of developers. In this case, the rationale is that if you have many developers that are working on a single software component, then I can foresee that maybe there will be some communication issues, because maybe the documentation is not perfect, or maybe because they cannot communicate because of other reasons. And then the idea is that in the 2013 there was this study from Ostrand and Bucher, in which basically they assessed whether the number of developers has an impact on software defect prediction. And in the end, they were able to find that there was a positive correlation between using this metric and the good performance. So they just say, yeah, you should compute it. But so at this point, I still cannot answer your question. So basically, that is actually also my question. So if someone asks me which predictor should I use, actually at this point in 2020, there's no silver bullet. So basically, the idea is that you should try to compute as much, as more software metrics as possible, as many software metrics as possible, because the point is that many studies demonstrated that they are very orthogonal. So there are some software projects in which you should use the process metrics. There are some others in which you can rely only on the structural metrics, and some others in which the developer metrics they work very well. I mean, think about, for example, a case in which we have only a small software team in which there are only 3 developers. In this case, it's very hard that the developer metrics will tell me anything, because I basically have only 3 developers that are working on all software components. So basically, my machine learning model will not be able to distinguish which software components are defective. I mean, I could be able to do it only in the case in which there is one developer that is very, very bad, and then the other 2 are good developers. But generally, it's really hard that this metric will help you. And also, similarly, think about the process metrics. So the problem of these metrics is that they work only when the process is very well defined. So in my experience with industry, I saw that there are some companies that they use Git by applying all the good practices, but then there are also some other companies that they don't use it properly at all. So basically, in these cases, it's very hard that you will find anything useful in applying the process metrics. So one of the most recurring problems we had in software defect prediction in the last 50 years, because it's a story of 50 years, is about the machine learning pipeline. So basically, all the papers I showed to you, they were developed before machine learning was so famous. So nowadays, when we talk about machine learning, is kind of a buzzword. But think about that. Most of the papers I told to you, I presented to you, they were presented in the beginning of the 21st century, so at least 10 years ago. And machine learning at that period was not a buzzword. I mean, we didn't have Alexa, we didn't have any technology that we are applying at this point. And so one of the main threats of those papers is that it's possible that the experiments were not performed in the way we would do it today, just because at this point now we know much more about machine learning. So in the second part of this presentation, I will not provide to you many details about machine learning per se, but only about how to use it in software defect prediction. So first of all, this pipeline matters. So I assume that you already know what is machine learning. So the idea is that you have this is just an example. So let's say that you have a classifier that is able to infer which is the language of a sentence. So the idea is that we have the first sentence that is in English, the second one is in English, third one is in Dutch, the fourth one is in Dutch. And then what we do is that we call these sentences the training set. Now, for these sentences, we don't have only the independent variable that are the sentences, so the words, but we have also the dependent variable that is the language of these sentences. Now, the problem is that we like to create a model that will help us in understanding which is the language of these two sentences. We can use these sentences to validate our model, and this is why during the presentation we talk about the set. So when I talk about the set, it's actually about a series of instances that I can use to validate my model. So first of all, when we talk about machine learning, I told you that the data pipeline matters. And one of the issues that you can see while reading some part of the previous work is that all these details, so the details about data processing, the details about the machine learning pipeline, they are not very clear. And this is a serious threat for studies in software defect prediction. And in this case, I talk about what is the origin of data, how the missing values were imputed. Did these people scale the data or not? Did they clean the data? So did they, for example, remove the outliers in their code, in their instances, in their datasets? Did they apply any feature selection? It's possible that some of those models are just overfitted. So maybe, and think about that, if the machine learning pipeline doesn't work, I mean, it's not really well conceived, then comparing metrics doesn't have any sense. And another question, for example, is about data balancing. I mean, was the data set they analyzed well balanced or not very well balanced? And think about it. The only way to try to understand whether this pipeline really works is to have a look to the code, have a look to the data. And this is why, at least in software defect prediction, but I believe in software engineering in general, is very fundamental that all the data are publicly available. Because in any study that is about machine learning, if you change a really small detail, then you change the final result. It's possible that you provide the details about the data preprocessing, and you provide the details about everything that is here, but data balancing. By changing only a small, changing only a small parameter there, I could basically infer completely different results. And this is why, and I think that, I mean, on the one hand, I believe that, yeah, this is a problem in science in general. But on the other hand, I also believe that the software defect prediction community is doing quite well, because there are many data sets that are available, and I know that people are working on also on other data sets. So I was telling you about training and testing. So about the fact that you can use some instances for training your model, and then you can use some instances to verify whether your model works. So in software defect prediction, when we do something like this, we say that we are applying a within project solution. So we are creating a within project model. The real problem of doing this is that, of course, when you try to apply, you try to create a winning project model, at the beginning, you should try, I mean, you should label your data, because otherwise you will not know what is the dependent variable in your training set. So basically, it means that if tomorrow I develop my new brand new software system, I cannot use any software defect prediction model, just because at the beginning I need to label, I need to understand where are the bugs. So this is a problem that you have when you try to apply within project models. It's true that there are some studies that basically assess that if you like to do it in practice, you need only a few months to create a good model, because then the number of issues will be stabilized, and you can just start using your model. But in any case, the problem that you have with the within project defect prediction is that, at least at the beginning, the new projects do not have enough information to train these bug prediction models. For this reason, during the years, several alternatives were proposed, and one of them is called the cross-project. So the idea is that we have many past projects. So let's say that I'm the other Formula One team. So I'm Ferrari, and I have some software defect prediction models. The idea is that maybe I can try to use the models from the previous years in which Ferrari was winning a lot, and trying to use these models for training. So to get information to understand in the new instances that I have for my brand new car, if I have defects in those instances. So the idea is that I just take all the information from the past projects, and I use these instances to create the training set. Then I use this training set to create a model, and then I use this model to assess the effectiveness of my instances. In this case, we say that I apply cross-project defect prediction. The real problem is that in many cases, cross-project defect prediction doesn't work. And the problem is that basically there is too much, in some cases, there is too much data heterogeneity. So let's say that I'm Ferrari, and then I would like to use the model that I mean the instances that I have from 20 years ago when Michael Schumacher was driving. So the problem is that this data is completely different from the data that I have right now, because the cars are completely different. And so basically means that I cannot rely on those those instances. Another question that you have in machine learning is actually how to select a machine learner. If you look to, there are so many classifiers. I mean, there are classifiers that are based on regression algorithms. Some of them are based on decision trees, on the Bayesian theory, but really there are a lot. And then the real question is, which one should I use in software defect prediction? Which one should I use for my application of machine learning to software engineering? And actually, I believe this is still an open question, because and I believe that the only thing that we can assess right now is that this choice has a strong impact on the performance of your model. So basically, now the only thing that I can tell you is that there's no model, there's no classifier that you should use a priori. Indeed, as assessed by the study of 2015, the performance can increase or decrease up to 30%. So it's really, I mean, it's something that is significant, depending on the type of classification algorithm that you apply. But actually, another nice research point of view is about combining these classifiers, because not only they perform in a different way, but also they are able to correctly classify different instances. For example, this is a paper of, actually it's 2018, it's not 2017, in which the authors were able to, I mean, they tried to understand whether the classifiers are complementary. And actually they found out that there are some specific bugs that you can correctly distinguish by using only a particular classifier. For example, in this case, they were able to state that, for example, for a support vector machine, 8% of the bugs were correctly detected only by this classifier. And for an ABS, almost 18% of the bugs were detected only by using this classifier. It means that the other classifiers were not able to detect this bug. So basically, this means that not only the performance are different, but also they are able, different classifiers are able to detect different bugs. So maybe, yeah, we should think about using them together. But I would like to give you like a final tip to how to do it. And actually, the only way, and this is something that I also tell to my students in machine learning, is just to have a really strong pipeline, a really strong validation pipeline that will allow you really to understand which is the best solution for your dataset. So the idea is that in general, you should use different classifiers. You should tune these classifiers. You should really have a look to the classifiers you are trying to use, and then you should try to understand how they are composed, which are their parameters. You should not use them as a black box. At least you should try to spend some time in understanding what is the inner working. And I assure you that if you spend like 1 hour in trying to understand how a super vector machine works, then you will be rewarded at some point, just because you have a grasp of how it works, and you cannot understand why it doesn't work. I mean, at least you can try to infer it. And the idea is that you should try to, and then you should select the classifier that works the best in your validation. That is the best on the data that you have. A priori, I can tell you that there are some techniques that are using that are called ensemble techniques. That, for example, they combine different classifiers. That could be a nice solution in all cases, but again, there's no silver bullet. The only thing that you can do is to validate your model. And then the next question is, yeah, but how should I do it? So the real problem, and this is another real problem of some defect prediction studies, is that the validation in many cases is very bad. So the 101 for validating your model is k-fold cross-validation. The idea is that you take your dataset, you split it in 10 folds, in which, at least if we talk about software defect prediction, the number of folds is well distributed across the folds. And then what you do is that you use all folds but one as training set, and the remaining one as test set. And then you repeat the experiment 10 times in case you have 10 folds. So let's say that you have 5-fold cross-validation, means that you create 5 folds, you use 4 for the training set, 1 for the test set, and then every time you change the test set, and you repeat the experiment 5 times. But yeah, I mean, as I was telling you, this is the 101. So there are also more advanced techniques, but this is the minimum that you should do. At least when we talk about some data that have no historical, so they are not historically related. So for example, when we investigate a single snapshot of a software system, k-fold cross-validation is something that we can do. Of course, another main rule of machine learning in general is that you should never use future data to validate the past. So let's say that you have 10 years of data. You should never use the data of yesterday to try to validate something that was developed 10 years ago, because this doesn't work. I mean, it's not a real case. The validation should always represent a real case, because otherwise you cannot trust your model. And this is one of the drawbacks of machine learning in general. The only thing that you can do to trust in your model is to validate it properly, because otherwise, okay, creating a machine learning model is very easy, but creating a good one is not so easy. And then when you have this validation, I mean, after you apply the validation, you will have some performance metrics, and you will have some results. And the first thing that you should try to have a look is the confusion matrix. So this matrix gives you the information that is about the true positives that you have in your system, the true negatives, the false positives, and the false negatives. So the idea is that if your predicted class, for example, is a yes, so in this case, we are talking about the buggy components, and then the real class was a yes, then we have a true positive. And yeah, we have the opposite relation when we have a true negative. So for example, when we predict as not buggy a component that was not buggy. But then we have two kinds of error. The first one is about the false positives. So basically some components that were predicted by our model as buggy, but in the end they're fine. And then the opposite case, so the false negatives, so basically components that are buggy but were predicted as not buggy. Now, having this confusion matrix is easy to compute many metrics. So if you have a look also on Wikipedia, there's this nice representation, this nice plot. You can compute many different metrics, and the idea is that you should try to understand which is the most suitable for your data set. So generally, for software defect prediction, you can never trust the accuracy. One of the issues that you have is that basically in software defect prediction, you have a few components that are defective, and most of them are just clean. But when you analyze the accuracy, in the end, you're analyzing, if you have a look to the formula, you're analyzing the true positives and the true negatives. But the real problem of defect prediction is that you have many false positives and false negatives. In this case, you will never understand how many there are. So there are several alternatives. One thing that usually works is to evaluate to the F1 score, so also called the F measure. And another option is to use some more complete metrics, such as the Matthews correlation coefficient and the area under curve ROC, or the area under curve precision recall. So just to provide you an idea, the fact is that if you use something that is very well structured as the Matthews correlation coefficient, basically you have a full overview of what is happening in your system. You have only just one metric that is in a range between 0 and between -1 and 1, that will tell you whether your model actually works. And I think that is one of the best options that you can trust. Also consider that the more metrics you compute, the better it is, but always try to understand them. So have a look to them. Try to infer whether, given the problem, try to have a look to the formula. Try to infer which one is the best for you. It's possible that in your particular case, you don't want false positives. So in this case, you have to analyze which one is the best metrics, best metric for your context. In case you like to reduce the number of false negatives, maybe you can use another metric. So for example, in this case, I would use the false negative rate. But it's really a matter of trying to understand what is the most well suitable metric for your context. So in case of software defect prediction, the best option is the Matthews correlation coefficient in my point of view. So actually now I have a question for you just before the break. And the question is, so at this point, what do you think is the factor that the most affects the performance of a machine learning pipeline for software defect prediction? It's the data balancing, the classifier selection, the data heterogeneity, or the feature selection that you apply. Just let me create the questionnaire. A, B, C, D, and yes, these are the options. So just to complete this part, I think that it's I mean, when you read about software defect prediction, I usually tell to my students that, okay, if they really wish to start working in this field, it's really a matter of reading a lot of material, but then also try to be very critique about all these works. So really trying to understand whether the researchers made mistakes, or basically, I mean, it's just that it's an incremental process. So basically, nowadays we know that we have some knowledge that in the past people didn't have, and we should try to reassess everything. But the real problem is that to do that means that we have we must have the data, we must have freely available data, we must have freely available code, because otherwise you really cannot compare anything. And this is one of the issues you have when you try to assess the past. In many cases, I mean, at least 20 years ago, open science was not really a hot topic with respect to what you have right now. I mean, right now, if you publish a paper that's about defect prediction and you don't release the data, yeah, in most of the cases, I mean, if you submit it, I think that in most of the cases will be just rejected. Yeah, so you can see real time also who is giving which words. That is totally fine. But I mean, it's totally fine just for this round, because actually you are all right. So yeah, this was a tricky question. So basically, at this point, it's just about telling you that all these different factors, they all matter. I mean, there are many studies that are about the impact of data balancing, the impact of customer selection, the impact of data heterogeneity, the impact of feature selection. And the idea is that what matters is the whole pipeline. And in your pipeline, every single aspect should be really considered, because otherwise you cannot really trust your data and your results. Just a last slide before the break. So for this reason, as I was telling you, first of all, always have a look to the confusion matrix. It's the only way to really have a feeling on what is happening in the background. Then consider that bug prediction is an imbalanced problem. Do not use accuracy, because otherwise you will not you will not I mean, you will not have some good I mean, it's possible that you will have some good performance, but in the end they don't tell you whether your model is good. So basically, let's say that you have a model, I mean, a data set in which you have 99% of false instances. So basically 99% of files without any bug. Then a really stupid model that just says no every time. So just answer no to any question that is about the bugginess, will have a 99% accuracy. But a priori, you can understand that this is not a good model. You should not use it. But if you trust the accuracy will tell you that this model is able to achieve 99% accuracy. So this is why, at least in this case, you should not use it. And the only way to understand it is really to have a look to the metric you are using, and to have a look to the matrix. And then, at least in case of bug prediction, please use something that is a bit more consolidated. For example, use the Matthews correlation coefficient, or use the area under curve ROC, or use the area under ROC precision recall. So now I guess that we can have back, and then I will give to you some information about the other guys, the ones that we don't like a lot. So Alex, I presume that we can have a 5 minutes break, 10 minutes break.
Well, usually we take a quarter an hour, but given the time, and if there is no major objection from the audience, I would probably suggest to go for a 5 minutes break.
Okay.
Okay, so let's take a 5 minute break. I will stop the recording now.
Yeah. Did you resume it?
Yes, the recording is on.
Okay, thank you. So the second part of this seminar is about the guy that we don't like, the bad. So actually, the bad is the guy that always says, yeah, okay, but machine learning is easy. It's basically, yeah, you have many tools, you have many tutorials, you have many frameworks. So at the end, creating a machine learning pipeline is something that you can do in just 5 minutes. So now I will show you a specific bad example about how you should not use machine learning. And I provide to you also some food for thought to implement your models. So now we are moving a bit from defect prediction to code smell detection. So basically, when we talk about code smells, we talk about symptoms of poor design or implementation choices. Think about that code smells has been around since Fowler wrote this book, the refactoring book, that is very well known in academia, but also in industry. Is one of the main books about software maintenance and evolution. And the reason why people care about these code smells is that actually these code smells, they have an impact on the comprehensibility of your code. And actually, they also increase the fault proneness, and the change proneness means that the software components that have these smells, in the end, they are more buggy than the other ones. And then to detect these smells, you have many tools. For example, one of the most well-known is SonarCube. It's a tool that integrates many code smells, and actually give you advice on many kind of different issues that are related to technical debt. Now, when we talk about this kind of tools, they are usually based on heuristic. So the idea is that you have an heuristic that you like to apply. So it's basically a formula that you like to apply, and based on some metrics, you derive this formula, and then you have a specific threshold. For example, if we talk about code class, that is basically a really large class that you should split. The idea is that, for example, we could try to measure the lines of code of this class, and then we would just say, okay, so the class is too long, then we should split it. But the problem is that, first of all, different tools, they provide different results. So at the end, there is low agreement between all these tools. And then basically, if you are using many of them, you don't know which one to trust. Another problem is that these tools they are based on thresholds. So basically, for example, when you use when you try to infer what is a good class, and you have a metric that is based on the lines of code, then the threshold is okay. How many lines of code are needed to define a software component as a God class? And think about that. This threshold, it's something that comes from experience, or it's something that comes from the common wisdom, or from past projects that you already analyzed. It's not written in stone. And so it's possible that you cannot apply these thresholds to your project, and then basically you cannot trust the results of these tools. Now, the idea that came out a few years ago is that, okay, but maybe we can use code smell, we can use machine learning for code smell detection. And if you think about it, the rationale is good, is great, because basically it's kind of the same application we saw before. So you have some predictors. For example, for a God class, we could think about the lines of code. Then we can use a machine learning technique that is able to distinguish which components are God classes and which are not. And basically is able to distinguish smelly and not smelly components. And then in the 2016, there was this paper that is very well known about comparing machine learning techniques for code smell detection. Now, there are many things that I like of this paper. For example, and when I talk about the characteristics of this paper, just think about what I told you in the first part of the lecture. So basically, one of the first things I told you is that when you like to use machine learning, you should try to use as many more classifiers than is possible, because a priori you really don't know which one is the best one. Okay, they used 16 machine learning algorithms. That is a really huge number. And then they apply them with and without boosting. So boosting is just an ensemble technique. So basically it means that they use these machine learning algorithms with and without steroids. And yeah, this is great. And then they also perform the parameter tuning. So basically it means that for each machine learning classifier, they really spend a lot of time trying to create the best model as possible. So this is something that was great. And actually, they tried to verify whether the components were smelly on 4 different code smells: God class, data class, feature envy, and long method. Now, just to give you an idea, think about it. 2 of them are based on the class, and the 2 others are based on the interaction between the methods of the classes. So the God class and data class are about the characteristics of a class, a complete class, while feature envy and long method are about the interaction between the methods of the class. So now I have a question for you. So do you think that, so let's talk about code smell. Actually, yeah, there's a type. So it's not a code design, but a code smell. Do you think that they are symptom of defects, poor design choices, poor implementation choices, or security issues? So I have another question for you. And yes, let me create it. And you have 30 seconds to answer. And actually, I don't want to reveal who did it correctly and who didn't. So I will just move on. But you will know the answer because I will tell you. Okay, so just to recap, code smells are symptoms of poor design choices or poor implementation choices. So if your answer was B or C, then it was correct. But, so going back to the previous work, the one that we are analyzing as the bed, is that it had two main issues. First one is about distance selection, and the other one was about data balancing. So as I told you, when you perform machine learning, the only way to trust your model, if you would like to put it in production one day, is to basically validate it correctly. If you don't, there are no other ways to tell you whether your model is good or not. So basically, we had a look to the dataset they used, and we observed that there was a pretty skewed distribution of instances. So in that dataset, 2/3 of the instances were classified as no smelly and 1/3 as smelly. What does this mean? And why it's a problem? So it was a problem because in reality, the number of code smells is much lower. So basically it means that this kind of validation does not represent the real world. Because if you have a real world in which the number of code smells in a software system is something like 5% or 1%, then your validation should represent this real world. Otherwise, you cannot trust that your model will work. I mean, your model maybe will work, but in a model, in a world in which 1/3 of the instances is smelly, that is basically a really poor system. I mean, means then the problem is another, is that your system is very smelly, so it means that the maintenance and maintaining your system is not so easy. And then yes, we had a look to this. I mean, we keep having a look to this data set and this paper, and basically we verified that in that paper, most of the classifiers were actually very good. They were really well performing because they were performing 95% in terms of F measure. And actually, the main outcome was it doesn't matter which classifier you select, because most of them they had 95%. I mean, all of them they had at least 95% of F measure. There were some of them that were like 99% accurate. So basically, it means that yeah, it really doesn't matter which one you select. Everyone will be good. And actually, I mean, if true, this could be a great news, because basically it means that, okay, machine learning is really the solution for code smell detection. But then in 2018, we performed a study. And actually, our goal was trying to understand whether the difference in I mean, we tried to understand what is the difference in the metric distribution of smelly and non-smelly instances in the 4 datasets that were exploited in the reference work. And then what we did is that, first of all, we extracted the most relevant features in those datasets, and to do that, we applied the gain ratio. And then we did we compared the metric distribution of smelly and non-smelly instances. And for doing this, we applied a statistical test. For example, in this case, we applied the Wilcoxon test and the Q delta. And surprisingly, first of all, we saw that only 1/3 of the features were relevant. And this is a problem, because basically it means that 2/3 of the features were actually useless. And then another problem that you have when you create a machine learning pipeline is that you should have the smallest set, I mean, the smallest number of instances of the features in your dataset. Because usually these features, they correlate to each other. So if you want to have a nice model, then you should try to reduce the number of features. And then by applying the info gain, we verified that only 1/3 was actually relevant. The others were correlated, so they should have been removed. And then we also by analyzing the smelly and non smelly distances, the distribution between these metrics, we also found that there were statistically significant differences between the metrics in the two sets, so the set of the smelly instances and the set of the non smelly instances. But what does this mean? Basically, this means that it's in this kind of data set, it's really easy for a machine learning algorithm to distinguish distances if they are statistically significant, they are different in a statistically significant way. So what we tried to do is to create a better data set. So the idea was, okay, so let's presume that the dataset that we saw is, that was in the previous paper is not realistic, because in reality we know that the boundaries between the smelly instances and the non smelly instances are much stricter. Then what is the performance of machine learning techniques when trained on something that is a bit more realistic? For example, a case in which the boundary between these instances is a bit smaller, a bit smoothed. And then to do this, we did it in a really simple way, maybe too simple. So basically, what we did is to just take these the data sets, because we already knew that. Two data sets were for classes and two others were for methods. So basically they could be combined, but they were not combined. And then the idea was that we would like to create a data set that could reduce the differences in the metric distribution, and we would like to create a data set that is less balanced with respect to the one that we saw. And so we just combined these two. We just combined pairs of data sets, and we created 4 new data sets, one for each code smell. So in the first case, we combined God class and data class to create a new God class and data class data sets. And then in the second case, we combined the data sets for feature envy and log method to create 2 new ones. And in this way, we created data sets that in a really simple way could reduce the distribution, the difference in distribution between the metrics. And then we saw that there was a strong decrease in performance, up to 90%. And then the best classifiers were J48 and random forest. There are many cases in which random forest is a very well performing algorithm. And actually, the choice of a machine learning approach is highly relevant for the effectiveness of defect prediction, the code smell detection. So basically, in sum, this provides you an idea on what you should and you should not do. So what you should do is to really validate your models in an accurate way. I used to tell to my students that the only shield you have to protect your model and to protect your model with respect to people that will say that your model doesn't work is your validation. The stronger your validation, the better, the most you can rely on your models. Another thing is that you have really be careful about how you create your test sets. So in machine learning, we have one rule. Basically, you can do whatever you want on your training set. Really, whatever you want. So you can decide to clean or not data. You can decide to apply or not feature selection. I mean, I always use it, but it's up to you. You can decide to balance or not your data set. It's up to you. It's really up to you. But what you should never do is to touch your test set, because if you touch your test set and as you start screwing up your test set, then you will not be able to trust your results. Doesn't matter if you have a 90% of accuracy or 1% of accuracy. You cannot trust it. So the final part of this presentation is about the ugly. So at this point, we are saying that okay, machine learning is cool. You can use it in many applications. There is a lot to know about, but in the end, at least for defect prediction, it seems that we can use it. Now, if we move to code smell detection, we say, okay, but we can use it, but we really must be careful about doing it, because something that you have to think about from the slides is that the performance decreases to up to 90%. So basically it means that some models that were performing really good, after a while were performing horribly. And so what we tried to do after this study was to try to understand, okay, but so after that we were able to infer that machine learning basically is not always the best choice. Can we say that heuristic-based approaches are useless? I mean, the ugly guy will tell you, okay, these heuristic-based approach are from the 90s, don't use them. But then the point is that should I use a machine learning approach or not? I mean, are machine learning approaches better or not? And then based on the study that you already saw, we showed to you that machine learning, this study showed to you that machine learning could be a valid alternative. But basically we say that, you should really test it in a more realistic data sets, because otherwise you cannot say anything. And then we tried to understand, okay, so let's make a new study. Let's try to just take the two techniques, the machine learning techniques and the heuristic-based techniques, and let's try to compare them. Then we used a data set that was large enough, so it was composed of many releases, 125 releases that were belonging to 13 software systems, just because we like to reduce the threats to validity. And then these data sets were belonging to different, they had different sites, large time application domains, and they were large enough. So they were composed of 8,500 manually validated code smells. So it means that someone manually validated them label by label. And they were belonging to 5 different types of code smells. And indeed, we analyzed 3 code smells that are about large and complex code, and 2 that are about object-oriented programming violations. So the first ones are about classes and analysis of classes and methods, and the other ones are about the relationship between the methods. And then what we did is that we took a state-of-the-art heuristic-based approach that is called the Decor. We computed some metrics by using this tool, and then we created our data set, and then we were able to, for all classes of our data set, we were able to infer which metrics, which instances, which components were smelly. And then we did the same by using machine learning, and we basically verified that the best approach was to use naive Bayes. That is a really simple classifier with respect to the others. And then what we did is to perform cross-validation by employing a tenfold cross-validation, the 101 I told you before. And then we reperformed where we recomputed the number of, we recomputed, redetected the code smells in the same data set. So we just compared machine learning with Decor. And in this case, an Bayes-based approach with Decor. And we computed some metrics, so precision, recall, F-measure, and MCC. Now, again, a question for you. Which metric at this point do you think that is the most suitable for defect prediction and code smell detection? So it's the precision, the recall, the F-measure, or the MCC? of course, you have 30 seconds to answer. I will not show you the other screen because otherwise it will be, I mean, it's not really designed for privacy. So I will give you 30 seconds and then I will give to you the answer. By the way, I will have a look to the answers later. So at this point, I can tell you that the best metric in this case is the MCC, because actually also in this case, we are talking about an imbalanced problem for which basically MCC provides you the full overview on the results you have. So it's the metric that you should use. You can use it together with the DF measure that provides you some a different but still a complementary measure. And then if you like to go in details, you can use the other metrics, but they're not very, they are not mandatory. So, and then we had a look to the results, and yeah, the results were something like this. So basically, now you see the results only for two smells, for God class and spaghetti code. And basically, we saw that the difference, is pretty much negligible. And actually, the machine learning-based systems, they have low precision, lower precision, higher recall, lower F measure, lower MCC. So basically, okay, using a heuristic-based approach is not so bad. And then we computed the overlap to try to understand whether these two techniques were complementary. And we saw, and this was a bit surprising, that there are 30% of the instances that are correctly predicted by both approaches, but then there are 20% of instances that are detected only by the machine learning approach, and 60% that are detected only by DECOR, the heuristic-based approach. So maybe at some point we should combine them. And then, yes, by having a look to the heuristics, we saw that the recall is in line with the previous studies, but the precision was extremely low. So it means that we had many false positives. But then we tried to understand something about the machine learning models. So we tried to compare these models for naive Bayes with an optimistic, a pessimistic, and a random classifier. So basically, an optimistic classifier is the one that always say yes, a pessimistic always say no, and a random classifier is just a random classifier. So basically, you have random answers. And then we verified the number of false positives and the number of false negatives. And yes, it was surprising. It was really surprising to see that if we have a look to the false negatives, we don't have many false negatives. But there is a reason for this. If you have a look to the metrics, the reason is that basically in code smell detection, when you analyze code smell in general, there are really few instances that are true, that present a code smell. So the number of false negative is very low. And indeed, if you have a look to the pessimistic classifier, in this case, seems to be a really good solution, just because here there is an approximation, but the type 1 error was something like 0. Something. So basically, if you have a classifier that will always tell you this class is not smelly, in the end you will have better performance than an AI-based solution. And this provides some food for thought. And yes, so the idea is that, first of all, if you would like to summarize, first of all, the heuristic-based approach need further improvement. Then machine learning seems not to be suitable for code smell detection, and the highly imbalanced nature of the datasets lead to poor results. So as last part, I will just show you what we tried to do, but really briefly. So the problem is that, as I told you, these data sets are really screwed. So there are a few instances that are smelly, but most of them are not smelly. And then you have to try to understand, and this was one of our concerns, whether you can use a balancing technique or not. So we did a large study, which basically we employed many data balancing techniques. and we tried to understand whether they could improve the results that we had. And actually, our results were a bit ugly. This is why I say the ugly. I mean, they were not bad, they were ugly. That is actually worse. Because basically, we just saw that, for example, in case of God class, you can see from this plot that the results between oversampling, not balancing, and smooth, they're actually the same. So just to provide you some information about this plot, the elements that have the same color, that are grouped with the same color, they have basically they are the same in terms of statistical significance. So they are basically they have the same performance. So in this case, we see that there are 3 data balancing techniques that perform really badly, but in the end they perform similarly. So there is a one class classifier and a data balancing technique that is based on undersampling, another one that is based on cost sensitive classification, and then there are 3 others. One is based on oversampling, one on no balancing, and one on smooth, that are actually performing the same but are a bit better. But what is bad about this plot is that basically applying oversampling or applying no balancing is statistically the same. And actually, we had the same result on another code smell as well. So then basically we came up with the final result that no balancing technique is statistically better than the others. And basically there's no significant evidence that applying data balancing is useful. So on the one hand, we know that the data sets are imbalanced, but data balancing is not a solution at all, at least for this kind of a problem. So I will be delighted if you have a question, comments. In any case, please consider that yeah, usually I was available in Den Bosch, but in any case, you can contact me via my mail or my 2 email, or you can just contact me via Microsoft Teams. I have yes, you can just contact me with your TUE Microsoft Teams. Comments? Otherwise, my lecture is over.
Thank you very much, Dario. It was really interesting, and I hope that everybody has enjoyed this lecture. As Dario says, you can always find him per email or on his Twitter or on his website. As you obviously know, this lecture has been recorded and it will be made available both at Canvas and on our YouTube channel.
Yeah, it's fine.
Thank you very much for your attention. Dario, thank you very much for the lecture. Goodbye.
Bye.